Hi everybody. In this video we're going to look at a kind of new thing called a piecewise defined function. So what is a piecewise defined function? Well, as it says here, piecewise defined function is a function which has different rules for different parts of its domain or subsets of its domain. And so here we've got an example. This particular piecewise defined function is commonly called the absolute value function because it takes an input, any x value, and it only spits out what you might call the magnitude of that value. Okay, it doesn't care about positive or negative, it'll just spit you back the number without the positive or negative. Okay, but this is what it looks like when you try to write one down. It's got this normal f of x equals, then you've got this curly bracket, and inside this curly bracket, you've got multiple lines of expressions, and also attached to each expression is some kind of interval. Okay, so what does that mean? What does that actually mean for us? Well, our function's split into two parts. Okay, the first part, this one here, is saying f of x equals negative x whenever x is less than 0. And the second part is this one here, saying that f of x equals x when x is greater than or equal to 0. Now that's still, a whole bunch of jargon, okay? But if you were to sort of say that in plain English, what it's saying here is that the first part means when x has a value less than 0, I have the rule f of x equals negative x. And the second part means when x has a value that is greater than or equal to 0, I have the rule f of x equals x, okay? And I mean, we can work with this function in exactly the same way that we work with other functions. So we can just do f of negative 2, okay? And how would you work something like this out? Well, you go back and look at your rule. The value of x that we're inputting into our function is less than 0, okay? Which means to evaluate our function, we need to use this part of our function because the value that we're putting into it is less than 0, and our function is defined to be negative x whenever x has a value less than 0. Okay, so if we're going to work out f of negative 2, you'd do negative, and then you'd replace x with negative 2. Okay, because that's like saying f of x equals negative x. There's that negative here, and x is negative 2. Okay, and if you work this out, negative 2, you end up with positive 2. Okay, you do the same thing for negative 7. Okay, you end up getting negative of negative 7. Again, we're using the first part of our piecewise function because the value of x that we're putting in has a negative value. Okay, negative of negative 7 is just 7. Okay, what about something like 0? F of 0. Well, because our value of x is equal to 0, that corresponds to the second part of our piecewise function because our function is equal to x when x is greater than or equal to 0, for which this value is equal to 0. Okay, so that means to evaluate the function at 0, we have to use the other expression. So we just substitute x. It's not negative x anymore, it's just x. And we don't do anything with that, it's just 0. Okay, what about something like f of 1? Well, our value of x is greater than 0, so again, we're going to be using this second part of our function to work it out. And in that case, you just replace the x with 1, and you end up with f of 1 equal to 1. Okay, you can play around with this yourself, start inputting values into it, and you'll notice that no matter what value you put in, it'll always give you a positive number back. And that's why we call it the absolute value function, because it just gives you the absolute value of the number that you're putting in. Absolute value just basically means the value of the number without any positive or negative attached to it. Okay. But what we'd like to do is graph this. What would a graph of this piecewise function look like? Well, here it is. Okay, you can see it looks a bit weird, but it's basically just two graphs drawn at the same time. Okay, so here on the left-hand side, whoops, we've got the graph of f of x equals negative x. Okay, notice that our graph is drawn on the interval x is less than 0. So x is less than 0 is from here, oops, from here that way. Okay, so that's x is less than 0. Okay, so it's sort of like us defining a function. So let's say we've got a function f such that our domain is from negative infinity to 0, going on to R, and our function has the rule f of x equals negative x. Okay, that's basically what the first part of our piecewise function is. Okay, it's just a function that's been defined on a particular domain. The domain here being from negative infinity to 0, or if you prefer, for when x is less than 0. Okay, so that's that graph here on the left, this purplish looking line. The graph on the right is just the graph of the other part of the function. Okay, the graph of just f of x equals x, or if you prefer, y equals x, which is just that, you know, linear graph that goes through the origin, has a gradient of 1. And again, you could define just this part of the graph with the function f such that we go from 0 to positive infinity onto R. We've got f of x equals x. Okay, so you've basically just got two functions, that one and that one, combined into one. Okay, each function or each rule of the function is defined for a specific domain, and then when you graph it, you just graph each of those for each of those particular domains. Okay, cool. So what's our strategy when we sketch these kinds of things? Well, general strategy is as follows. Okay, so first of all, just mark on the x-axis the places where your intervals split. Okay, so in the previous example, your interval splits at this special value, 0. Okay, that's where you stop drawing one graph and you start drawing the other. Okay, so those are the places you're going to mark off on your x-axis first. Then, once you've done that, you're just going to treat each piece of your piecewise function as a separate function, one at a time, just sketching each one at a time. Okay, and the guidelines for sketching each piece are as follows. Okay, so you first of all just work out your intercepts or critical features like you would normally when you sketch a particular type of graph. The other thing you have to worry about though is because we're not sketching over the entire Cartesian plane, we're going to be stopping our drawing at a particular endpoint. You need to determine what the endpoint is for each of the pieces. Okay, and I'll show you how to do that in a second. Right, then you just sketch each piece within each interval for which it's defined. And finally, just double check whether or not the endpoint is included or not. If it's included, you sketch in with a closed circle, a filled in circle. If it's not included, you draw an open circle. Okay. Sometimes the pieces of your piecewise function will sort of match up and connect to each other, but that won't always be the case. If they do connect to each other, you don't need to draw a circle because you definitely know it's going to be defined at that point. Okay, so let's have a look at an example. So we've got this piecewise function here. It's got 3 pieces, as you can see. All right, so our first step here is to just sketch in a Cartesian plane and mark off the intervals, okay, where your function splits. I'll do that in another color. When I do this here, I'm going to draw some dotted lines, but these are not technically part of your drawing of your graph. These are just for us to visually see where our intervals split. Okay, so there's 0 and 1 here. Normally what you would do is you just write those numbers on the x-axis. You don't need to put the dotted lines. It's just for us to see. You could draw it with pencil and then just rub it out later. Okay, so our first piece that we have to sketch is this one here, x plus 3 for when x is less than 0. So that's going to go in this portion. Whoa. In this left-hand portion of our Cartesian plane. Okay, so that's going to have the rule basically y equals x plus 3. Okay, so that should be very clear to you that that's going to be a linear graph. It's going to have a y-intercept of 3 and a gradient of 1. So we can mark in our y-intercept straight away because that's pretty easy. So let's say 3 is here. All right, and that's also an endpoint. How do we know? Because our interval stops at 0. If I was to substitute 0 into here, we get 0 plus 3, which is 3. So that's our endpoint. And you can see it's an endpoint because it lies on this dotted line where our interval is going to split and transfer over to the next part of our function. Okay. What other things do we have to work out? Well, we know it's going to be a linear graph, gradient of 1. So it's going to go down like this. It's going to go through the x-axis and go off forever back that way. Okay, so we need to work that out. That's your x-intercept. How do we work that out normally? You make y 0 and solve for x. So if you do that, you end up getting negative 3. Okay, so that's the first part of our piecewise function sketched in. All right, now we're ready to move on to the second part, which is this graph here. F of x equals negative x plus 3 for the interval 0 to 1 inclusive. So that corresponds to this interval here. Okay, so within this interval, we're going to be sketching the graph of y equals negative x plus 3. Okay, again, that should be pretty clear to you that that's going to be a linear graph. It has a y-intercept of 3 and a gradient of negative 1. All right, so y-intercept of 3. Bang, you can just put that straight in. That's already there. Okay, and we have to determine the other endpoint though. Okay, that's the left-hand endpoint. There's going to be another endpoint somewhere on this vertical line, x equals 1. So how do we determine that? Well, we just substitute that x value into our function. So we're going to do y equals negative, okay, what's our x value? 1, so negative 1 plus 3, you end up getting 2, okay? That means our endpoint is going to have the coordinates 1, 2, which we'll say is about here. We draw a closed circle because we are including that endpoint as indicated by the less than or equal to symbol, and you just draw a line connecting your endpoints together, okay? Because it's a nice linear graph, we can do that. Notice though, also here, the first and second parts of our piecewise function actually join up at this y-intercept of 3. So that's pretty nice. Sometimes that won't happen, so you just got to be careful when you draw in your circles, just make sure they're closed or open. All right, the last part is going to be drawn on this interval here. Okay, and all the way off to infinity. Okay, so what are we drawing there? Well, our graph will have the rule y equals x squared as indicated by this part of our piecewise function. That should be pretty clear to you that that's just going to be a parabola. Okay, now normally parabolas have a turning point down here at 0, 0 at the origin, and it would go up like that, something like that off to infinity. Okay, but we're not going to be drawing that part in because that's outside the interval for which this part of our function is defined. Okay, so first steps first, let's work out where we're going to start drawing our graph. Where is that left endpoint? Okay, so we know we're going to start drawing our graph when x equals 1. So to work out our endpoint, you substitute x equals 1 into this rule of our function. We get y equals 1 squared, which is 1. Okay, so that means when x equals 1, y equals 1, and so our endpoint is at 1, 1, which we're going to say is here. We draw an open circle because we're not including that point on our graph, because it's strictly greater than. And then you draw something that roughly looks like a parabola. You can sort of imagine drawing a parabola going through the origin, comes up like that, and then continues off up like that. Okay, so this is quite a complicated piecewise function. It's got 3 parts, but you can see each individual piece isn't actually that hard to work with. Okay, so you split your axis into the intervals that you're going to be working with. You draw each piece of your function within each interval, working out your endpoints, working out your intercepts if you need to, and then you just put it all together. Okay. lastly, sorry for making this such a long video, but you can actually graph them on your CAS. Okay, so here we've got it graphing it on the Casio. Now, when you graph it, I'll actually switch to the... Give me one moment. We'll switch to my emulator. Yes, we'll keep all our markings. Let's go to our emulator. Okay, so let's see how we can graph it. Don't mind that, that's just some old things. Clear all. Okay, so let's see how we can graph a piecewise function. So with your keyboard, go to Math 3, and you should see this button over here. Okay. Now, if you want two parts to your function, you just click it once. If you want multiple parts, you just click it as many times as you need to introduce those multiple parts. So let's click it a second time. So we've got 3 parts to put in. So what we're going to do is we're going to graph this on our CAS. Okay. So in the first part, we're going to have x plus 3. And that's defined for when x is less than 0. The second part has a rule negative x plus 3 and is defined between 0 and 1, inclusive. And lastly, we've got for our third part is f of x equals x squared, and that's defined for when x is greater than 1. Okay, you can hit enter, nothing's going to happen, just to make sure that you've typed it in. Now to graph it, you go to your little graphing icon. All right, and you highlight this. Oops, what happened? Go away. It's a bit hard to do on the computer, but there you go. Highlight, drag, and it will graph it for you. Okay, now my zoom's a little bit off, so let's change that. Let's go to auto, see what happens. That's a bit annoying. Let's zoom in at this part down here. So let's go change our y values. Let's go negative 5 and 5. There we go, look at that, perfect. Okay, so you can see 3 parts to our function. The first part, y equals x plus 3. The second part, y equals negative x plus 3. And the third part, y equals x squared. Okay, and notice that that matches our drawing that we did over here. Okay, cool, so it's not that hard to sketch piecewise functions on your calculators. All right, we'll stop there. That's it for piecewise functions. So review the video, make sure you leave a comment if you're unsure about anything, and I'll see you next time.